Thank you very much.
I'm starting recording.
Okay. Okay. 1 second. And I think you can see my screen, right?
Yes.
So as Max summarized, today's talk is about the dimensionality analysis of atomic environment representations and also the implanted neural networks for mission learning interatomic potentials. That's the name of the workshop, right? These works that I did on my postdoctoral research, one is at Harvard University and the other one is the University of Warwick. So you can see from the web page, workshops web page, and it shows that I am in University of Warwick, but I moved to Biovia R&D in Dassault Systems, my current position. Today I will talk about my earlier works, so it's not related with the this position or any other products of it. So as I mentioned, I will talk about the dimensionality analysis, but we also did the sensitivity analysis, but I'm not covered that part today. So when we think about machine learning interatomic potentials, and yesterday also you listened to from the other talks, we start with the prediction of the properties of the materials, right? So what we would like to do actually, on the left-hand side here, you can see the structures, for example, a crystal structure, or maybe more complicated structures, like proteins, for example, 7,000 of atoms, really large systems. So the idea here is predict right-hand side. So that's where it starts. Either electronic properties or structural properties, like energies, forces, charts, band structure, band gaps, or band of states. So we predict it. What's the model is, as you can see in the equation at the center, we try to predict the T target for a specific property equals the F function in optimization on top of a model, which has some parameters. We don't know whatever it is currently, but we can decide that, right? So machine learning interatomic potentials, when we are talking about this, important part is the energies and forces, because we would like to consider the potential, right? So here what we can see this problem as the model is can be a regression model, a kernel model, or a neural networks, or simply a linear models or also work. So VB, the parameter set of these models are what we call the descriptors, fingerprints, or in other older methods, let's say, or in chemistry, for example, or biology, they call QSARs, quantitative representations, or the property representations, for example, QSPRs. So what we, in machine learning interatomic potentials, actually we see this picture in a different way. I will change the title and the arrow. So in machine learning potentials, this is actually representing the potential energy surface. So what we are trying to predict is using exactly the same model, but we would like to predict the potential energy surface of a specific material. So we can use it as a potential, interatomic potential. That's where everything starts. So the crucial part is on the right-hand side now, the electronic and structure properties are the most important part is the energies and forces, not the other parts we will not care about currently. So what are these models? I'll talk about the VB and MA today, and how we consider these. Okay. So in a big picture, we recently put it together some classifications. Material representations can be classified in property, chemical, physical properties in the red column, topology-based descriptors on green part. Blue part is the atom neighbor density. There's quite a lot of descriptors there. So will not talk about the red part. QSIRs, they are in 80s. There's a lot of different descriptors there, but we not use it in machine learning interatomic potentials. And mostly what is captured in the community is the user graph topology representation, or either atomic density representations. For example, the CGCNN which is and the Schnet at the column you can see from the top to the bottom. There's Coulomb matrix, CGC, and Schnet on the topology side, connectivity graphs. So these are graph convolutional neural networks that's used. Or the Schnet is simply use this graph topology on the left-hand side in the box that bond distances, three-body angles, information, but all are based on the graph, for example. So I'll not also talk about that part, but we are mostly considered on the atomic neighborhood densities for the environment representation. So it's the bottom part. So all of these names, Y spectrum, ACSF, atom symmetry functions, yesterday you see that one in neural networks. SOAP also, smooth overlap of atomic positions. And the others, Chebyshev polynomial representation of ANet, for example, and recently atom cluster expansion, ACE, also will be covered in this workshop in this week, I think, other talks. So all of them are based on atom density representation of the bottom part, as you can see. So we represent this B in terms of the neighbors around specific atoms at the center. And we can represent, for example, with the radial distribution function, RDF. So GR, for example, on the bottom equation can be RDF. And we can extract this information in terms of the vector BR. So today you will use in the tutorial a smooth overlap of atomic positions. So here I just summarize it. So we represent this atomic neighborhood by putting Gaussians on atomic positions. So we define the rho R in terms of the Gaussian on the top equation and build a SOAP kernel. So SOAP kernel is basically the overlap of these densities. However, this density, this kernel for different chi atomic neighborhoods and the overlap matrix inside it, you can see these two integrals actually. So the outside is the R actually for all of the R's that for every rotation, for example, in the system. So we try to capture all of the rotations per over two chi and chi prime neighborhoods for an atom. So we'd like to capture that inside the kernel so we can represent all the structure. So this kernel can be used in similarity analysis or in Gaussian approximation potential. But today we will not use it in that way. However, this integral actually is very expensive because, as you can imagine, you need to do all these rotations to make the kernel invariant under the symmetry operations. So instead of the elegantly Albert Bartok and Kaboshan's work in the reference below, so they found a solution to this very expensive problem. They've used the basis for the density. So you can see this CNLM is the coefficient, GN is the radial function with a polynomial times the spherical harmonics. Then you can actually expand it in the power expansion using these coefficients, CNLMs, and build your kernel actually. So here today we will use this P vector, the coefficient vector, as a descriptor vector, and we will build a neural network. So instead of symmetry functions, as you did yesterday, we will use another descriptor, but we will use to build a neural network on top of it. So the question is, okay, let me go back. We expand this from the density with the radial basis times the spherical harmonics, right? So we expand it within the known NLM radial and the angular part of it, these parameters, angular momentum. So, but we don't say anything about the structure yet, right? I mean, we expect that we will give these parameters and expand it and capture all of the structure. So, but the question is, which features or which elements of this expansion actually is relevant in our data set? Are we actually expanding too much information? And why this is important? These are the questions. Why this is important? Because if you use a very large vector to describe your systems, all of the systems available, there's a possibility that in your data set, actually, you don't need that much of information, and the rest of the information actually doesn't capture anything and return to be a noise actually in your model at the end of the, because we will optimize this at the end. So the model that we use to reduce this number of elements and select the meaningful ones is CUR decomposition. So today you will use that one. In this decomposition, we expand this data set X, which have these rows of these vectors for every atom in your structure and all of your structures. So we build a huge matrix. We select certain columns. We put these columns into C matrix. R is the row matrix, and U is the reconstruction matrix. As you can see at the bottom, for example, error, E is calculated with the X minus CUR. Is reconstructed X, which is a tilde. We don't know whether it's exactly the same, but we calculate the error. So what we did is calculate the scores. How we did this score calculation is we do the SVD transformation, get right a singular matrix B, and calculate the columns multiplied with 2 for each of them, the square of these vectors, and found PC actually. So build this C matrix with the highest score columns, orthogonalize the other columns, and then calculate the error. Okay. So this is kind of expensive. Even if you try to calculate, for example, a couple of hundred structures with around 10 to 20 atoms inside, you exceed like 10,000 of rows. And for so, for example, we will use like around a couple of hundred elements, vector size. So this is really expensive and turns out to be not memory efficient. So what today we will use is, actually we will discard the scoring mechanism in a different way, and we discard totally the error calculation. What we will do is we calculate the principal component decomposition, because when we do this principal component decomposition, we know that the target, the principal components equals to the X times W, which are these maximum variant eigenvectors of the X transpose X, which is, we know the X actually. So we can get this maximum variance for all of these eigenvectors. Instead of calculating the errors, we will check only the maximum variances for the selected columns. And this turns out to be really cheap to calculate. And I will show it to you in the tutorial also. So we will see quite good corresponding values with the error and variances. So we did this similar analysis without using the PCA part, but we calculated in the large data sets from NOMAD data sets, ANET data sets, I think yesterday that's already shown, the titanium oxide one, and the GAP data sets also, silicon data sets. So we use this analysis CUR decomposition for different descriptors. I didn't explain the ACE or ACSF, but you already know the ACSF and the SOAP also. So here the graph shows different color shows the different data sets, and we use the parenthesis shows the number of elements in the vector, the descriptors. And as you can see, SOAP has quite a similar kind of relevant part of the descriptor. For example, after 75%, there's negligible information. As you can see, it's turned to be flat. This is also the same in the ACSF. This is a standard symmetry function dataset that's in the papers. After 85, we don't have any information. And these are the really large datasets. There's molecules, many alloy structures. Silicon dataset includes surface information and amorphous and all sorts of structures. So thinking about it, there's some, for example, a part that doesn't capture anything. Okay, we would like to reduce it down. And we did that and analyzed. So the next part of my tutorial will cover the machine learning interatomic potential part, the INN. So let's get back to this picture. We would like to understand how this model can be selected. We select neural networks. Okay, neural networks is there, we can use that, but there's some catch on the training. And I was in the talk before this one, in the session, and there was a discussion about how to train the neural networks, right? So, okay, so we started actually from an actual material problem. You would like to understand the lithium battery works and with the silicon anodes. So the idea is silicon has an order of magnitude theoretical capacity. So it's really attractive in the material field. You can see the image of the early stage and the later stage of a lithiation of crystal silicon. So bottom part is silicon is a crystal silicon, upper part has a lithium source. But in intermediate parties, actually, there's an amorphous phase, and this phase extends. And from this TEM experiment, you can see that there's a different contrast, which is different concentrations. Experiment doesn't say what they are, but we know that from the density function theory results also that there's different kind of amorphous concentrations are there. And you would like to understand the diffusion coefficients. So we need a potential, and there wasn't any at that moment. And we would like to develop it. So we use machine learning interatomic potentials, neural networks. So this title says implanted neural network, but this picture doesn't show the implanted part. I will come to that in a minute. So we use a standard artificial neural network. The input part is the angular and the radial symmetry functions, ACSF, and the predicts the one atom's energy. But we don't know one atom's energy, right? From the underlying model, for example, DFT. We know the total energy, E total, and we sum up the atomic energies. So here you can see that each layer X, actually Y, J, K is the layer, can be expressed in this equation at the bottom with n nodes times weight, Aij, times the input vector, plus a bias, Bj. These are Bj and Aij's are actually weights. We fit them. So in the second layer, for example, whatever the output of this layer will be used as an input. So if you check this Aij times the input, you can see that it's an expansion, not linear. So we are trying to find weights with this input. Input is the symmetry functions, and we put linear expansion on top of it, plus some shift. And the F is a tangent hyperbolic. We put some nonlinearity, and then we do the same basis expansion. We do every layer a basis expansion until we find a meaningful atomic energy, which we don't know actually. We know the total energy of this structure. Okay, so we build a data set, a lithium amorphous data set. You can see on the left-hand side, the lithiation process of the silicon with a small amorphous set is calculated from CSTEM. Pink atoms are lithium. Whenever the lithium concentration increases, you can see that the bonds are breaking. And we use a large data set. Within that data set, and then we train this neural network, showing the total energies. We first train just a traditional one. So what we found is overfitting immediately. Even in the thin data sets, we don't use, for example, every single image of the molecular dynamic simulation, but we get the every 100 or every 200, depending on the temperature. We extract quite a small data set, thin data set, but even in that data set, you can see the test error immediately goes up. So normally, the traditional way is in neural network society or in machine learning society, let's say, select this one, the line where the test error does not go up anymore, because we know that even if we train in the green one, the data set's error goes down. You are overfitting some structures, but your model cannot capture the general representation of the potential energy surface of the system. The other tests error go up. So another approach is, why not put the data set from the test data set to the training back, because we are overfitting, right? Let's put them because we are not capturing the system. But that's not a good idea. And the other problem is, in in that line that I showed you the point, when we get that one, okay, let's use this one. It seems more general neural network. But when we try to calculate the equation of state, the diamond silicon, we see some bigger dash, this total energy, which is not physical. There's no energy below the basin. There's no minimum energy than ground state of silicon, right, in dataset. But it is actually, but it was from the lithium side. Lithium sites change the energies here. How this can happen? Because some of the parts here in overfitting. So we decided, okay, we need to use a small data set just for crystal. We built this stat, the top part, the blue neural network. We only train the crystal silicon and show the silicon structure. And then add new layers, add the amorphous structures, for example, show all these crystal and amorphous structures, train our neural network, but fixing the blue part, blue nodes, which means that we fix the AIJs and the bias parameters of the N nodes while we increase the number of nodes to N. And then we also did it for lithium part because we have two neural networks, one for lithium, one for silicon. And when we combine them, we also add the new layers. For example, for silicon one, that's the red nodes. And for lithium one, that's the green nodes. We increase them, but fixing the previous parts. We call this implanting these neurons, implanting the pre-trained neural networks. And it helped. And you can see the result here. The test data goes down without going up. And yes, the energy, that the dashed line here, corresponds to the green, some of the green lines in the previous ANN. But you know that there was some kind of overfitting which actually does not capture the physical system. So now the ANN training and test data set doesn't have this overfitting. We calculated again the equation of state and found that actually we don't see this figure anymore because the crystal part of it is trained very well, but it doesn't mean that the other parts are discarded by overfitting this part. Or try to capture, for example, amorphous part. Maybe the ANN try to do that one because try to lower all of the errors actually for all of the structures in your data sets. You don't have a control on that one. You can only say, for example, to the neural network that on the training, you weight, for example, structures picking by hand, right? You created your data set, but you know what is in your data set and you select, okay, I want crystal to be perfect, and you increase the weight, turn it on, right? So the optimization will try to match that one, but discard the others. But this one doesn't do that. In this neural network, we do all these weights same. All of the weights are one for all the data sets. And then you can see this average error is 3.9 MeV. We calculate the long time scale molecular dynamic simulations up to 3.75 and at room temperature and calculate the diffusion coefficients using the mean square displacement error. And the actual diffusion coefficients for lithium and silicon quite match with the experiments, while the DFT and other potentials in the literature overestimates them. So this is the theoretical part of what I'm talking today. I will go to the slides. Thank you for my thank you to the collaborators and the funding. You can see the tutorial link here, and I will show you immediately. Should I answer the questions before tutorial?
I mean, first, let's see if we have any questions. So if anyone has questions on the theory part, could you please raise your hand? Yes, I already see one from Peter. So yeah, we have time. So if you'd like to go ahead and ask.
Okay, I can continue to the tutorial side.
Actually, it's up to you guys. I have a question, but I can discuss with Berk later on.
Is it a quick question?
Okay, let's go to. I don't think it's a quick one. So sorry.
Okay.
Let's go to the practical one.
Okay. I'll go a bit more on the tutorial side and maybe answer all the questions at the part and try to match 2020, but slightly exceed my time in the 20 part, I think. So you'll find this in the shared workshop in the deep note. So the tutorial starts with the content, as I mentioned, on the descriptor selection, the descriptors reduction of the elements and the neural network training in the INM model. So we'll use several packages. One of them is QP and the other one is PyTorch. So the original lithium silicon INN is developed in LuaTorch and is implemented in OpenKIM, and you can use LAMPS. But for this tutorial, because it cannot run here in this Jupyter notebook and there's some limitation on the resources, I will show the links to you so you can go and learn more about that. But here I will just use the PyTorch with a small data set. So you can run everything in this Jupyter notebook. There won't be any resource problem. So you can see the first part is just extracting the data set functions here. So I'll just skip through that part. So you can see this, for example, this ML data object here, which you can use to extract the data from the structures. You don't need to, for example, split the training or test data sets. The next part is the CUR that I mentioned, but we use these successive principal components selection instead of the scoring. This will be much faster. So you can run anything in this notebook without any problem, because normally you can exceed memory even at your laptop. When I use on my laptop, you can exceed several gigabytes of memory because you need to have all of the CUR metrics, including the input X, for example. So you have replicates of some extension of the matrices, so it will immediately extend the memory. But in this one, you will not. So the dimensionality analysis part starts with the silicon dataset gap potential. We extract this data from the extended XYZ file. You can get the total energies from the dense functional theory, and we will use we will shift these energies from the first one, which is the isolated atom energy. So everything will be shifted as the reference is the isolated atom. So the target energies will be shifted. And you can see the different structural types here. So we will use one amorphous structure, only one, because as I mentioned, there's some resource limitation here. So it can go immediately fast large structures. I don't want to do that one. We will use the already calculated DFT energies from this Lipatons silicon test framework and calculate this diamond BCC and FCC and using the ASC framework and generate the structures, extend the lattice, shrink the lattice and extend it to get this equation of state. And because we would like to calculate the bulk modulus at the bottom. So the next part is, as you can see, we extract here the amorphous and diamond part, but we will only use the amorphous one structure, the first one, as you can see here, from the data set and get the energies, and that's all. So once we build this data, we can use a small data set and shrink the vectors, get the reduced vectors. I commented on that part, but if you would like to download this notebook and run in at your other resources, HPC centers, for example, for really large data sets, you can run the CUR decomposition. And also we have the link in descriptor zoo here. So you can access the original code. This one is a slightly bit different. As I mentioned, it uses PCA instead of the normal scoring and the error calculation.
Berk, do you mind if I interrupt really quickly? It seems that the notebook hasn't been shared to the team, so nobody's, well, I think most people are not able to access it.
How can I do that?
I'm not sure. Maybe it should have.
It seems shared. No, not shared. It was yesterday. Okay, I'm sharing it. Okay, can you see that now? I remember it was yesterday.
Yes, now it says setting up. Okay. So
it says members of the team can also collaborate. Okay, and this was it actually yesterday, the same. Okay, I can see people now.
Maybe it's just a little glitch. Okay.
That was a glitch, I guess. I didn't touch the notebook after. Okay, so we will use the SOAP descriptor from the QUIP. You can check their documents to how this SOAP descriptor works, because there's other descriptors, but I just used a small definition here in this cell. We will use radial expansion, the largest n as 9, and angular one is also 9. These are the same in the paper that we published, sensitivity analysis paper, and the results that I show you in the presentation, this dimensionality reduction curves. This is exactly the same setting. We will only use this diamond BCC, FCC, and one amorphous structure, as I mentioned, one configuration here. So the others are 12. And build a huge matrix. This all data is one matrix for all of them. And you can see this matrix size is 768, even for this small system. And this can go really large. I mean, tens of thousands, and then your matrices are really, really large. And here you will run this model. The parameter here, error true, means that we actually calculate the CUR, the error. So I mentioned that I will show you the PCA version, the variance version, and the error, actual error calculation. So when you do this error calculation, you can see that even in the presentation I showed, after 75% SOAP descriptor, this slightly goes down, make a curve, and then turn to be really flat. Now it goes after 2% goes flat immediately, because the structures that we are putting is just the crystal structures. And there's one amorphous structure, but probably it's also because in the amorphous distribution of this silicon, that there are the closer atoms have this second peak, but the rest is turned to be far away. So if you know the radial distribution function, so maybe we are not expanding that much and don't need that many features. So when you do that, you can see a lot of this information is actually flat. And there's one more part, that if you check the variance, actually, that's in the PCA steps, every step we do the PCA again, using this shrinked matrix. We select one column, shrink the matrix, select another column, shrink the matrix, and do this every time and try to calculate. We calculate the variance and scale it, because it's, the variance is scaled to 1. Okay, so when you do that, you can see that it's really immediately goes down. Like around 50, for example, it's even 10 to the minus 6. After that, everything is negligible. Because if you exceed 10 to the minus 8, the actual error calculations turns out to be exceeding the floating point precision already in these machines, double precision, actually. So the idea here is you don't need to go through all of this expensive part. When you run it, it will take 2 to 3 minutes this box. Even it's a really small system, it will take quite a long time. But for the variance, it will be much faster to analyze. You don't need to do the error calculation, because we have the variance already at our hand, right? From the PCA, because we know this. We selected the vector, which is the eigenvector. We did the SVT transformation. We don't need to do the orthogonalization step. We don't need to do this matrix multiplication and scaling for the error calculation. So we will drop 2 of them. And you can analyze just this graph and select the values. So the second one is just, don't giving this error and compare actually the speed. That's why. So you can see that we can select 20 first, whatever the numbers are, we select these columns and build our vector. So here, for example, 140, 20, 250 are the most important columns. So you can shrink it more down if you want. So that's that part. We extend our the descriptor vector with the SOAP using 9 and 9 for radial and angular part, and then L numbers. But we found that we don't need to use the 450 elements of this descriptor for our data sets. We shrink down to 20, which is really fast for training the neural network. So the question was, why you can still use the 450, you will get a similar results. But we know that if you if you have really large number of features, elements in your vector, there's a course of dimensionality in the problem. You need to also have a more complex optimization at the end. We don't want to do that. You can shrink, for example, your neural network's node size now, because we don't need to put lots of descriptor elements. So the second part is INN. So this is basically the shrink down version of this INN package to PyTorch, and you can run everything here because the idea is simple. You build a neural network. Here, the layer part at the bottom is basically the PyTorch neural network module. So what I edit is the embedding part, implanting part here. Whatever you give as an implant underscore net underscore list, actually, whatever the networks there, we store the weights and biases. And we have this implant function. Before every forward, we implant these vectors to the position. So we fix these weights there always. If there's no neural network implanted, it will be run just ANN. So the training is similarly from the PyTorch. Again, we use the optimization. You can select the SGD or EDM optimization. It doesn't matter currently. We do this training, but every training step, there's the differences. There's an implanting part again. We fix because the optimizer stores the parameters here and updates them to the network side. So we feed forward first, but the optimizer also stores in weights. So we fix the weights in both sides, on the neural network side and the optimizer side. So optimizer cannot change that part. So this is where we push down all this, implanting the weights. And the select the training set, we actually doesn't put every point in diamond structure because we would like to see some whether wiggle or some shift happens. So if you do this training phases, we select the 0, 1, 2, 3, which are the diamond, BCC, ACC, and amorphous phases. We first, we don't want to use the FCC here. We just want to use BCC and diamond 0, 1, and put an amorphous phase to a bit make it complex, but not much. So we can train it in a couple of minutes in this notebook here. And we first do the ANN training using the 20 hidden nodes with the selected column number, which is also 20. And when you do this training, it will go a couple of minutes for the train using the learning rate here, around 20,000 training steps. So you can see this column here, RMSC actually is the training error. The test error is the on TX here, the input at the top, train 0 is the training input data, and TYs are the training data's targets, energies. So we are trying to get fitting all of this amorphous and everything in ANN because we don't have a choice, right? It's ANN, that's how it works. The test part is actually try to check whether this equation state, the points are correct. So you can see this, we have a better, for example, in everything, but not that good in the just the diamond silicon. So it's around 2, one of them is around 1 millieV. What we did in the INN is we select a smaller data set because we will not need to first train everything. We only train crystal diamond. So you can see 0.6, 0.6, that's what we expect in the first stage, and save this neural network. Then we train amorphous one, and we see another network, INN2. We again have the hidden size is 6, and we train that again 0.3 and 0. And then we implant 2 neural networks into one. But we increase the hidden size by 4. So which means that we have 2 6 neural networks, 12 plus 4, 16. So the total amount of the nodes are 16, but the first 12 of them are fixed with the weights that we put. First INN and this second INN2. The rest of them will be optimized. And the last INN3 actually, as you can see, is around 1 and 1, still similar-ish, right, in the ANN part. Again, these errors are quite similar, but the results have a difference. But this is a small data set, so if you run, for example, in different steps, you may find that ANN also can find good results, because that's how it works. But if you have a really large data set, you can't have a control. That's why we designed this method. So we calculate cohesion of state using the Barnagan method here. You can calculate again these descriptors from the calculator, SOAP calculator. Every step we feed the ANN, and then we feed the last step of the INN. And what you can see actually is here. In the blue one is INN here, blue energies. The red dot one is the ANN one. So you can see ANN also has a slightly bit of shift, because you can always have a slight shifts, because until you need to train more on these structures even at the last step, because what we try to do in the last step is, even we put this 2 neural networks weights in another neural network and try to hold them, there's other nodes that free, so you can optimize them, and it's controversial. So the cross, for example, weights need to be also optimized, because we feed the same information, but the different parts of the nodes generate different total energies, right? So it should compensate, and overall the additional nodes need to produce just 0 energies actually. So the other parts are hold, whatever they have the energies can be the correct energies. So this needs, the last step still needs in the INN a quite good optimization. But before that, you have perfect optimization for whatever you have. So the ideal optimization is in the INN is making your data set really small, train it very well, really small errors, and then embed it into another neural network. And train that one, again, a long time, without any overfitting. So the blue part, you can see that it's slightly shift, and the lattice constants turns out to be larger than the supposed to be. And then you can calculate the bulk moduluses, how they are shifted. So for example, it's 87.85 for ANN, the normal one, and we can get 80.77, which is quite close to the gap one. Of course, this is a really small model. You can extend it using the whole data sets, but it will exceed this notebook's capacity, I think. That's all I would say. I can answer questions, I think, in the last part. Yes.
Yeah, so just wanted a quick clarifying question here. So when you did a plot that made it really cheap to figure out how many features were important, right? There was the one that was very expensive, and then the one that was a lot quicker.
Yes. Mm-hmm.
Could you go to the second one, the one that was quicker? I just was curious. I didn't fully understand what it was you're plotting there.
Okay.
There's some
here.
There.
So this one, the actual error.
Right.
Let me show from the slides, show what that mean. So we are calculating the error at the left-hand side here. Okay, can you see my mouse?
Yes, yes.
Okay, so that's what we try to directly do that. But in the second one, the red curve, we actually calculate this W for every selection,
I see.
W1. Okay, so what's the differences? W1 is quite simple. There's this selected row. We already know that one because we calculated the V from this VD. But how that's the same thing. The vectors are here, so that's why we already has this information. But what we don't do is we don't do the orthogonalization of the other columns, and we don't need to rebuild the CU U especially, and do this error calculation because to do this, you need to store C, U, R is X again, but you also need to store the inverse of, because you need to U, and every time you don't want to build from scratch this matrix multiplication, you would like to store the X times X pseudo inverse somewhere. So you have multiple copies of similar size matrices in your memory to do this calculation. But now if we just remove that part, we don't need to do that. We can shrink the memory usage. And we don't need to do anything else on top of the SVD transformation, because whatever we have is enough. We will not do the principal component transformation. So we just get the variances and stop there. So this is what it does. You can check the code here that I embed into the CUR part. Let me show it to you. Yeah, here is the CUR rebuilding part. We will not run this CUR if you do not say error equals true. So we don't need to do actually this CUR decomposition because we don't need to error calculation. We just select the columns. So we calculate the importance again from the features principal components and normalization or standardization. The fitting here, just do the factorization is just do the selection every time using the PCA and get the model variances here with the scale, that line.
I see. Thank
so
you.
The variance ratio is from the PCA's this W, small w. We scale it with var scale because in current stage, for example, if we have the huge matrix, we know that the highest score one, let's say it's 0.8, for example, through the normalized one, the maximum is 1. The rest of the whatever there is 0.2. Okay, we store that 0.2. Next time we drop that column, we do the PCA again without transformation and just get the variance is the highest one, but scale with this 0.2. We multiply them until it goes to the 0, because we know that every selection and the total amount should be 1 because everything is normalized. That's the difference that I added here for this tutorial.
Thank you.
And
thank you.
this works quite similar. If you run the original dataset, and I did that in our paper, I get exactly the same curve, which is interesting because we know that from this calculation, the scoring here actually quite related with the maximum variance here, right? Because it's both of them uses the right singular matrix columns as the information. One of them is to use the eigenvectors, the other use for scoring. And orthogonalization doesn't affect that much because the SOAP bases are actually doesn't change that much actually here in the result, but it may for other descriptors.
Thank you for explaining that. Yeah, that makes sense now.
Mm-hmm.
Okay. Do we have any more questions? Yeah. Changbom, you can, or was that an accidental raised hand?
Hi. Yeah. Thank you for interesting talk. Yeah, I have two questions. One is the implanted neural network. The second one is about diffusion of ions. So first of all, as far as I understood, so you train independent neural network. Then later you immerse them into one neural network model. Is it right?
Yes.
Yeah. Then, but my question is because these weighting parameters and these parameters in the neural networks are trained independently. But after you train in the emerged model, then do they also change?
No, we fix the weights for that part. So you have one neural network, train it in normal ANN model, for example. You did that, I think, in a tutorial in Anode yesterday. Similarly, ANN, same approach. You train a neural network.
Yeah.
You get the RMSE quite good for your structure, right? So the idea of all of this picture is we define bias and AIJ weights, two of the weights, okay? So when we say we implant a neural network, we select the same number of nodes plus some additional nodes, but this same number of nodes weights are copied from the previous one, and we fix them. So the optimizer cannot change that part. So this means that when we feed the descriptor, the vector, that part, because if the input is same, that part will generate the same energies for atoms, right? But the rest of the nodes will not, because they are not optimized yet. If you do this, for example, train a neural network, implant it into a new neural network, extending your nodes, but do not change the data set, for example. What the network in the second one, the optimizer, will try to do is, since we fix the weights of a certain section, that will produce the correct total energies, but the rest doesn't, right? In the first steps.
Yeah.
So you will get really high errors. While we fixing these weights and they are producing the total, the atomic energy is correct and the sum of them will be correct, the rest of the part have to combine as a zero total energy, right?
Yeah, okay.
Okay, so you can extend this idea into adding more data sets. So you don't only train the previous data set, you can add plus new data sets, which then what it does is for different data sets, the first one, try to make that new nodes output zero because we are fixing the previous part. And for the new data set, it fixes optimize the new nodes.
I see.
That's how the picture changes. The normal ANN, we try to optimize everything.
No.
But we don't have any control which part will be fit better than the other. And you can easily change that by changing your sampling, which means you can change your data set and you can get a different ANN outcomes easily. You can, for example, put more amorphous sets than crystal ones, and because the optimization try to fit them more, because that's what in the data set, right? It will shift everything towards that side.
Okay, yeah.
Then people what do this, reduce the amorphous fitting weight and increase the crystal part by intuition, because they know that I want crystal better than amorphous. But that's a selection there. We don't want to do that. We don't want to select data sets. We don't know where the error will pop up, right? You can't find which one will be worse.
Okay, yeah, thank you. Second one is about diffusion. So when you see the mean scale displacement, do they for example the diffusion of lithium ions are similar to that of, for example, classical or force field simulation or Ab initio and simulation? Are they do they behave similarly, or or you see some different behavior of MSD? And second, another one is that do you see also finite size effect of the diffusion coefficient?
We didn't check that the finite size. I can answer immediately that one. I mean, we didn't reduce this structure that much. We always selected very large, a couple of thousand, because we know that the cutoff and we need to extend that cutoff where you can capture amorphous structures better. For example, in small systems in DFT, you don't have that good amorphous structure. It's just replicates itself because of the images, because you have really small structures, like here, for example. Let me show one. Here, this pure amorphous silicon, there's 64 atoms inside it. So it's basically the same image, right?
Yeah.
In the starting part. It is amorphous, but very limited in DFT calculations. But here, it's really long range, and we know that the long range effects are there. That's the one part. The other part is in the diffusion. That's why we calculate these diffusion coefficients. You can see that lithium DFT is overestimated. By the way, in the literature, I checked quite a lot before publishing this. We know that there is no diffusion for lithium over 10 to the minus 90, for 10 to the minus 9. So that line here, 10 to the minus 9, there isn't any diffusion above in the experiment. That can't be that fast.
No.
It's lower.
Yeah,
so
yeah.
You can see the experiment results are lower, and the NMR experiment is about 10 to the minus 10. So it can be fast, order of magnitude fast, but not that fast. But you can see the lithium DFT and lithium modify embedded atom methods, another traditional potential, for example, interatomic potential. That's not a machine learning potential, but it overestimates. And we did similar kind of mean square displacement error calculations. We fit the linear regime of the MSD. Our time step is quite small, by the way, 0.1 femtosecond. It's not 1 femtosecond. Because this neural network potentials needs a bit control over the time step.
So have you also
sorry, can we keep it to maybe one question per person?
Yeah.
And continue the discussion later, because we have one more very quick question from Edgar, please.
Yeah, thank you.
All right, thanks. I'll try and keep it quick. Thanks for the talk. I'm trying to get an intuitive understanding of how the implanted neural networks work. Is the idea essentially that one starts with a lower complexity and less flexible neural network, and then increasingly enhances its ability to fit more complicated hypersurfaces? And if so, what's the guarantee that as I increase the flexibility, it doesn't eventually start overfitting again?
There's no, right? I mean, this is basically in the starting part, the ANN, there wasn't anything. So this actually, you have a tool at your control. So you need to take care of for example, the increment every time. So if you see, for example, overfitting, you know that you have a far more step than the previous whatever you have in your neural network. You may, for example, increase the number of nodes really large. Then you again try to embed this, for example, the ANN idea again, right? Because if you increase the number of nodes immediately too large, the optimization try to fit everything to that side. You can't get rid of, for example, whatever you try to suppress there, will not be there anymore. Doesn't matter. You just discard that because it's enough nodes there to make the space expansion. So this should be really small steps, so you can control everything. So it's actually how in the mathematical point of view, it's greedy method. You select your data set and fit that data set, make that in your pocket, it's there, then again edit. You don't do, for example, let's rush from crystal to amorphous immediately. We did it here, but it's a really small data set. But you don't do that. You know that that's one of them is the ground state structure and the other one is something else, higher energy structure. There's nothing in between. You try to not even interpolate, try to extrapolate and try to fit two of them, and probably you'll not catch anything good in between. You know that from the physical intuition, the funneling, right? You start to put everything one by one, go there.
It's almost
Higher values.
iterative delta learning, no? Where you start with a simple model,
Yes.
and then increasingly, okay.
Because if you train the simple models and increase the steps, complexity, very intuitively, very small steps, you have the control over the overfitting, and you know that everything is trained and similar, right? Because there's no waiting anything in front of the data set, or you don't discard data or add data from the test data set because it's not fitted good. That's what other approach does.
Thank you.
All right. So thanks so much, Berk, for the tutorial and for the talk in the tutorial. If you'd like to continue the discussion, we can go on the Slack channel, for instance, or you can continue it, say, tonight at the poster session. But let's thank Berk again. And we will have a short break, let's say 5 minutes, enough time to get a tea or coffee, and meet back here at 10 past to continue with our next speaker. So see you in a bit.
Thank you very much, by the way. Thank you for everyone. I hope you enjoyed the talk.
Mhm.
And Vilo enjoyed the tutorial, by the way.